The vacuum of space is an unforgiving environment, instantly hostile to human life. In the first few seconds of exposure, the human body experiences a cascade of dramatic and often fatal changes. The most immediate of these is decompression, a rapid shift in pressure as the body goes from a pressurized environment like a spacecraft to the vacuum of space. Imagine a balloon inflated to its limit. Suddenly, the pressure surrounding it vanishes. The balloon expands rapidly, stretching its material until it potentially bursts. This is similar to what happens to the human body in a vacuum. However, our skin and tissues are far more resilient than a balloon. While there might be some swelling, the human body won't explode. However, the sudden change in pressure can cause gas bubbles to form in the blood and tissues. These bubbles can obstruct blood flow, leading to a condition known as embolism, which we'll delve into further later on. It's a race against time as the body attempts to cope with the rapid decompression and the ensuing chaos within its systems. While the immediate effects of decompression are dramatic, the most pressing danger in the vacuum of space is the lack of oxygen. Our bodies require a constant supply of oxygen to function. Without it, we experience hypoxia, a state in which our cells are starved of this vital element. Within 15 seconds of exposure to the vacuum of space, an individual would lose consciousness due to the lack of oxygen reaching the brain. This is a relatively peaceful transition, unlike the violent depictions often seen in science fiction. However, the danger doesn't end there. The body's involuntary systems continue to function for a short time, leading to a brief period of convulsions. These are essentially the body's last-ditch efforts to get oxygen into the system. Unfortunately, without a source of breathable air, these attempts are futile. As the body succumbs to the vacuum's relentless assault, more visible changes begin to manifest. One of the most striking is the swelling of the human body. This is not due to any external force pushing inward, but rather the expansion of gases trapped within our bodies. Imagine a scuba diver ascending too quickly from the depths. The decrease in pressure causes nitrogen bubbles to form in their blood, leading to decompression sickness, commonly known as the bends. A similar phenomenon occurs in space, but on a far more drastic scale. Without the pressure of the Earth's atmosphere, the gases dissolved in our tissues, such as nitrogen, begin to expand. This expansion causes the body to bloat, potentially to twice its normal size, especially in areas with more soft tissues. Contrary to popular belief, space itself doesn't have a temperature. Temperature is a measure of how fast molecules are moving, and while space is not empty, the density of molecules is so low that heat transfer is incredibly inefficient. This means that the human body wouldn't freeze instantly upon exposure to space. However, the lack of atmospheric pressure to trap heat leads to rapid cooling through a process called adiabatic expansion. This cooling effect is primarily through the evaporation of moisture from the skin and through respiration. Exposed skin would experience almost immediate frostbite, particularly in areas with thinner skin, such as the eyelids and lips. Interestingly, while the outer layers of the body cool rapidly, the core body temperature remains relatively stable for a short period. This is because there's no air or water in space to conduct heat away from the body's core. However, this internal heat is ultimately lost through radiation, which, while a slower process, is still a significant factor in the long run. Section 5. Ebullition, when fluids boil in a vacuum. One of the most gruesome effects of exposure to the vacuum of space is ebullition. This is the process where the boiling point of a liquid drops below its current temperature due to a decrease in ambient pressure. In the context of the human body, this means that bodily fluids like saliva, tears, and even blood can begin to boil in a vacuum. Imagine a pot of water simmering on a stove. As the pressure decreases, the water boils at a lower temperature. In the vacuum of space, the pressure is so low that the boiling point of water drops to a mere 98.6 degrees Fahrenheit, our normal body temperature. While the blood vessels provide some pressure containment, the fluids in the mouth and eyes would boil almost instantly. This wouldn't be a rolling boil like we see in a pot, but rather the formation of bubbles within the fluids themselves, causing significant discomfort and potential tissue damage. Section 6. The unseen danger radiation's insidious bite. Beyond the immediate physical trauma, the vacuum of space harbors a more insidious threat: radiation. Our planet's atmosphere and magnetic field shield us from a constant barrage of harmful radiation from the sun and other cosmic sources. In space, however, we lose this protection, leaving us vulnerable to the full brunt of this cosmic radiation. Exposure to high levels of radiation can damage DNA, increasing the risk of cancer and other health issues. While a brief exposure might not be immediately fatal, prolonged exposure can lead to a slow and agonizing decline, with symptoms ranging from nausea and vomiting to organ failure and death. The effects of radiation are cumulative, meaning that every second spent in space without adequate shielding increases the risk of long-term health problems. This is one of the biggest challenges facing future manned missions to Mars and beyond, as finding ways to protect astronauts from radiation during these extended journeys is crucial for their survival. Section 7. The final transformation: mummification or cosmic freeze. The fate of a human body left exposed to the vacuum of space depends on a variety of factors, including its proximity to a star and whether it's in the path of any celestial objects. However, in the vast majority of cases, the end result is either mummification or freezing. In the absence of air and moisture, decomposition, as we know it on Earth, cannot occur. Bacteria and other microorganisms that break down organic matter rely on oxygen and water to survive. Without these essential elements, the body would begin to desiccate, losing all moisture and becoming mummified. On the other hand, if the body drifts into the shadow of a planet or other celestial object, it would be exposed to the extreme cold of deep space. Temperatures in these regions can plummet to near absolute zero, causing the body to freeze solid. In this frozen state, the body could potentially drift through the cosmos for millions, even billions of years, a silent testament to the fragility of life in the face of the universe's grand indifference. Section 8. Ethical considerations and future exploration. The hypothetical scenario of a human body exposed to the vacuum of space raises numerous ethical considerations. As we venture further into the cosmos, the possibility of accidents during spacewalks or exploration missions becomes a stark reality. This begs the question, what protocols should be in place for handling such tragedies? Currently, there are no established international guidelines for retrieving and returning the bodies of astronauts who die in space. This raises ethical dilemmas concerning the dignity of the deceased and the emotional well-being of their loved ones back on Earth. As we continue to push the boundaries of human exploration, it becomes increasingly crucial to develop comprehensive protocols for handling fatalities in space. These protocols should address the recovery and return of bodies, as well as the psychological support provided to families and fellow astronauts. Section 9. Conclusion: the resilience and fragility of life. The human body, a marvel of biological engineering, is remarkably resilient in many ways. We can endure extreme temperatures, survive on minimal sustenance, and even regenerate damaged tissues. However, when faced with the unforgiving environment of space, our resilience reaches its limit. The vacuum of space, with its lack of oxygen, pressure, and protection from radiation, poses a constant threat to human life. Understanding the effects of this hostile environment is crucial not only for the safety of future astronauts, but also for appreciating the delicate balance that makes life on Earth possible. As we continue to explore the cosmos, let us remember the lessons learned from these hypothetical scenarios. Let us strive to develop technologies and protocols that prioritize the safety and well-being of spacefarers. And let us never forget the fragility of life, clinging to a pale blue dot in the vast cosmic ocean.